Lithium is a chemical element with the symbol Li and atomic number 3. It is a soft, silver-white metal belonging to the alkali metal group of chemical elements. Under standard conditions it is the lightest metal and the least dense solid element. Like all alkali metals, lithium is highly reactive and flammable. For this reason, it is typically stored in mineral oil. When cut open, it exhibits a metallic luster, but contact with moist air corrodes the surface quickly to a dull silvery gray, then black tarnish. Because of its high reactivity, lithium never occurs freely in nature, and instead, only appears in compounds, which are usually ionic. Lithium occurs in a number of pegmatitic minerals, but due to its solubility as an ion, is present in ocean water and is commonly obtained from brines and clays. On a commercial scale, lithium is isolated electrolytically from a mixture of lithium chloride and potassium chloride. The nuclei of lithium verge on instability, since the two stable lithium isotopes found in nature have among the lowest binding energies per nucleon of all stable nuclides. Because of its relative nuclear instability, lithium is less common in the solar system than 25 of the first 32 chemical elements, even though the nuclei are very light in atomic weight. For related reasons, lithium has important links to nuclear physics. The transmutation of lithium atoms to helium in 1932 was the first fully man-made nuclear reaction, and lithium-6 serves as a fusion fuel in staged thermonuclear weapons. Lithium and its compounds have several industrial applications, including heat-resistant glass and ceramics, lithium grease lubricants, flux additives for iron, steel and aluminium production, lithium batteries and lithium-ion batteries. These uses consume more than 3/4 of lithium production. Trace amounts of lithium are present in all organisms. The element serves no apparent vital biological function, since animals and plants survive in good health without it. Non-vital functions have not been ruled out. The lithium-ion Li+ administered as any of several lithium salts has proved to be useful as a mood-stabilizing drug in the treatment of bipolar disorder, due to neurological effects of the ion in the human body. Properties: atomic and physical. Like the other alkali metals, lithium has a single valence electron that is easily given up to form a cation. Lithium's low reactivity compared to other alkali metals is due to the proximity of its valence electron to its nucleus. Lithium metal is soft enough to be cut with a knife. When cut, it possesses a silvery white color that quickly changes to gray due to oxidation into lithium oxide. While it has one of the lowest melting points among all metals, it has the highest melting and boiling points of the alkali metals. Lithium has a very low density of 0.534 grams per cc, comparable with that of pine wood. It is the least dense of all elements that are solids at room temperature, the next lightest solid element being more than 60% denser. Furthermore, apart from helium and hydrogen, it is less dense than any liquid element, being only 2/3 as dense as liquid nitrogen. Lithium's coefficient to thermal expansion is twice that of aluminium and almost 4 times that of iron. Lithium is superconductive below 400 μK at standard pressure and at higher temperatures at very high pressures. At temperatures below 70 K, lithium, like sodium, undergoes diffusionless phase change transformations. At 4.2 K it has a rhombohedral crystal system. At higher temperatures it transforms to face-centered cubic and then body-centered cubic. At liquid helium temperatures the rhombohedral structure is the most prevalent. Multiple allotropic forms have been reported for lithium at high pressures. Lithium has a mass-specific heat capacity of 3.58 kilojoules per kilogram Kelvin, the highest of all solids. Because of this, lithium metal is often used in coolants for heat transfer applications. Chemistry and compounds. Lithium reacts with water easily, but with noticeably less energy than other alkali metals do. The reaction forms hydrogen gas and lithium hydroxide in aqueous solution. Because of its reactivity with water, lithium is usually stored under cover of a hydrocarbon, often petroleum jelly. Though the heavier alkali metals can be stored in more dense substances, such as mineral oil, lithium is not dense enough to be fully submerged in these liquids. In moist air, lithium rapidly tarnishes to form a black coating of lithium hydroxide, lithium nitride and lithium carbonate. When placed over a flame, lithium compounds give off a striking crimson color, but when it burns strongly the flame becomes a brilliant silver. Lithium will ignite and burn in oxygen when exposed to water or water vapors. Lithium is flammable, and it is potentially explosive when exposed to air and especially to water, though less so than the other alkali metals. The lithium-water reaction at normal temperatures is brisk but non-violent, as the hydrogen produced will not ignite on its own. As with all alkali metals, lithium fires are difficult to extinguish, requiring dry powder fire extinguishers. Lithium is the only metal which reacts with nitrogen under normal conditions. Lithium has a diagonal relationship with magnesium, an element of similar atomic and ionic radius. Chemical resemblances between the two metals include the formation of a nitride by reaction with N2, the formation of an oxide and peroxide when burnt in O2, salts with similar solubilities, and thermal instability of the carbonates and nitrides. The metal reacts with hydrogen gas at high temperatures to produce lithium hydride. Other known binary compounds include the halides and the sulfide, the superoxide, carbide. Many other inorganic compounds are known, where lithium combines with anions to form various salts, borates, amides, carbonate, nitrate, or borohydride. Lithium aluminium hydride is commonly used as a reducing agent in organic synthesis. Multiple organolithium reagents are known where there is a direct bond between carbon and lithium atoms, effectively creating a carbanion. These are extremely powerful bases and nucleophiles. In many of these organolithium compounds, the lithium ions tend to aggregate into high-symmetry clusters by themselves, which is relatively common for alkali cations. LiHe, a very weakly interacting van der Waals compound, has been detected at very low temperatures. Lithium has also been found to exhibit ferromagnetism in its gaseous form, under certain conditions. Isotopes. Naturally occurring lithium is composed of two stable isotopes, 6 Li and 7 Li, the latter being the more abundant. Both natural isotopes have anomalously low nuclear binding energy per nucleon compared to the next lighter and heavier elements, helium and beryllium, which means that alone among stable light elements, lithium can produce net energy through nuclear fission. The two lithium nuclei have lower binding energies per nucleon than any other stable nuclides other than deuterium and helium-3. As a result of this, though very light in atomic weight, lithium is less common in the solar system than 25 of the first 32 chemical elements. 7 radioisotopes have been characterized, the most stable being 8 Li with a half-life of 838 milliseconds and 9 Li with a half-life of 178 ms. All of the remaining radioactive isotopes have half-lives that are shorter than 8.6 ms. The shortest-lived isotope of lithium is 4 Li, which decays through proton emission and has a half-life of 7.6 times 10⁻23 s. 7 Li is one of the primordial elements produced in Big Bang nucleosynthesis. A small amount of both 6 Li and 7 Li are produced in stars, but are thought to be burned as fast as produced. Additional small amounts of lithium of both 6 Li and 7 Li may be generated from solar wind, cosmic rays hitting heavier atoms, and from early solar system 7b and 10b radioactive decay. While lithium is created in stars during stellar nucleosynthesis, it is further burnt. 7 Li can also be generated in carbon stars. Lithium isotopes fractionate substantially during a wide variety of natural processes, including mineral formation, metabolism, and ion exchange. Lithium ions substitute for magnesium and iron in octahedral sites in clay minerals, where 6 Li is preferred to 7 Li, resulting in enrichment of the light isotope in processes of hyperfiltration and rock alteration. The exotic 11 Li is known to exhibit a nuclear halo. The process known as laser isotope separation can be used to separate lithium isotopes, in particular 7 Li from 6 Li. Nuclear weapons manufacture and other nuclear physics uses are a major source of artificial lithium fractionation, with the light isotope 6 Li being retained by industry and military stockpiles to such an extent as to slightly but measurably change the 6 Li to 7 Li ratios even in natural sources, such as rivers. This has led to unusual uncertainty in the standardized atomic weight of lithium, since this quantity depends on the natural abundance ratios of these naturally occurring stable lithium isotopes, as they are available in commercial lithium mineral sources. Occurrence astronomical. According to modern cosmological theory, lithium, as both of its stable isotopes lithium-6 and lithium-7, was among the 3 elements synthesized in the Big Bang, though the amount of lithium generated in Big Bang nucleosynthesis is dependent upon the number of photons per baryon. For accepted values, the lithium abundance can be calculated, and there is a cosmological lithium discrepancy in the universe. Older stars seem to have less lithium than they should, and some younger stars have far more. The lack of lithium in older stars is apparently caused by the mixing of lithium into the interior of stars, where it is destroyed. Furthermore, lithium is produced in younger stars, though it transmutes into 2 atoms of helium due to collision with a proton at temperatures above 2.4 million degrees Celsius. Lithium is more abundant than predicted in later generation stars, for causes not yet completely understood. Though it was one of the 3 first elements to be synthesized in the Big Bang, lithium, together with beryllium and boron, are markedly less abundant than other nearby elements. This is a result of the low temperature necessary to destroy lithium, and a lack of common processes to produce it. Lithium is also found in brown dwarf substellar objects and certain anomalous orange stars. Because lithium is present in cooler, less massive brown dwarfs, but is destroyed in hotter red dwarf stars, its presence in the star's spectra can be used in the lithium test to differentiate the two, as both are smaller than the Sun. Certain orange stars can also contain a high concentration of lithium. Those orange stars found to have a higher than usual concentration of lithium or but massive objects, neutron stars or black holes, whose gravity evidently pulls heavier lithium to the surface of a hydrogen-helium star, causing more lithium to be observed. Terrestrial. Although lithium is widely distributed on Earth, it does not naturally occur in elemental form due to its high reactivity. The total lithium content of seawater is very large and is estimated as 230 billion tons, where the element exists at a relatively constant concentration of 0.14 to 0.25 parts per million, or 25 micromolar. Higher concentrations approaching 7 ppm are found near hydrothermal vents. Estimates for the Earth's crustal content range from 20 to 70 ppm by weight. In keeping with its name, lithium forms a minor part of igneous rocks, with the largest concentrations in granites. Granitic pegmatites also provide the greatest abundance of lithium-containing minerals, with spodumene and petalite being the most commercially viable sources. Another significant mineral of lithium is lepidolite. A newer source for lithium is hectorite clay, the only active development of which is through the Western Lithium Corporation in the United States. At 20 mg lithium per kilogram of Earth's crust, lithium is the 25th most abundant element. According to the Handbook of Lithium and Natural Calcium, lithium is a comparatively rare element. although it is found in many rocks and some brines, but always in very low concentrations. There are a fairly large number of both lithium mineral and brine deposits, but only comparatively few of them are of actual or potential commercial value. Many are very small. Others are too low in grade. The U.S. Geological Survey estimates that in 2010 Chile had the largest reserves by far and the highest annual production. One of the largest reserve bases of lithium is in the Salar de Uyuni area of Bolivia, which has 5.4 million tons. Other major suppliers include Australia, Argentina and China. In June 2010, The New York Times reported that American geologists were conducting ground surveys on dry salt lakes in western Afghanistan, believing that large deposits of lithium are located there. Pentagon officials said that their initial analysis at one location in Ghazni province showed the potential for lithium deposits as large as those of Bolivia, which now has the world's largest known lithium reserves. These estimates are based principally on old data, which was gathered mainly by the Soviets during their occupation of Afghanistan from 1979 to 1989, and Stephen Peters, the head of the USGS's Afghanistan Minerals Project, said that he was unaware of USGS involvement in any new surveying for minerals in Afghanistan in the past 2 years. "We are not aware of any discoveries of lithium," he said. Biological lithium is found in trace amount in numerous plants, plankton, and invertebrates, at concentrations of 69 to 5,760 parts per billion. In vertebrates the concentration is slightly lower, and nearly all vertebrate tissue and body fluids have been found to contain lithium ranging from 21 to 763 ppb. Marine organisms tend to bioaccumulate lithium more than terrestrial ones. It is not known whether lithium has a physiological role in any of these organisms, but nutritional studies in mammals have indicated its importance to health, leading to a suggestion that it be classed as an essential trace element with an RDA of 1 mg/day. Observational studies in Japan, reported in 2011, suggested that naturally occurring lithium in drinking water may increase human lifespan.